Chapter 8, Section 3, Digging Deeper, Formation of the Universe, Solar System, and Planets. The Big Bang Theory. In the previous two sections, you examined two different size systems, our solar system and then the larger Milky Way galaxy. In this investigate, you used one of the largest scale models known to science to demonstrate how the universe is expanding. You also investigated how scientists track the motion of objects in the universe. The Milky Way galaxy formed about 10 billion years ago and is one of billions of galaxies in the universe. According to a popular theory, the universe itself formed somewhere between 12 and 14 billion years ago in an event called the Big Bang. This is known as the Big Bang Theory. Big Bang makes it sound like the universe began in an explosion. However, it did not. Scientists call the beginning of the universe time zero. At time zero, the universe consisted almost entirely of energy. The energy was concentrated into a volume smaller than a grain of sand. The temperatures were unimaginably high. Then the universe expanded extremely rapidly. As it expanded, the temperature dropped. As the temperature dropped, matter was formed from some of the original energy. Cosmologists are scientists who study the origin and dynamics of the universe. They consider the presence of matter and energy in the universe today and how it may have changed over time. Cosmologists think that most of the matter in the universe was formed within minutes of time zero. Initially, this matter was too hot to form into atoms. After a few 100,000 years, the temperature of the universe dropped to the point where atoms could exist. The atoms were mostly hydrogen and helium. Eventually, under the force of gravity, these atoms began to clump together. They clumped into clouds of gas, which in time formed the first stars. As more stars formed, they grouped together to form the earliest galaxies. The expansion and cooling that started with the Big Bang continues to this day. Evidence of the Big Bang. Scientists point to three major lines of evidence for the Big Bang Theory and an expanding universe. The first of these is shifts in the wavelength of light produced by distant galaxies. This phenomenon is known as the Doppler effect. You experienced the Doppler effect in the investigate when you were swinging the noisemaker. You probably noticed a relationship between the pitch of the noisemaker and its movement. The pitch grew higher as it approached you and then dropped suddenly as it passed by you. You may have had a similar experience with the changing pitch and the tone of the siren of a passing emergency vehicle. In Figure 1, when a police car is coming toward you, the pitch of the siren is increased. When it is moving away from you, the pitch is decreased. Sound occurs in waves. When a moving object producing a sound approaches you, the sound waves are compressed, causing wavelengths to decrease. The distance between wave crests becomes shorter. This causes the pitch of the sound to become higher. The pitch of a sound is related to its wavelength. The higher the pitch, the shorter the wavelength. As the object moves away, the wavelengths of the sound waves increase and the pitch drops. The longer the wavelength, the lower the pitch. Light also occurs in waves. As a result, the Doppler effect can be used to determine whether a star or galaxy is moving toward Earth or away from it. Light from a star or galaxy can be detected as a spectrum of colors. You will learn more about the spectrum of light in a later section. Shorter wavelengths of light are blue or violet in color. Longer wavelengths of light are red. If a star or galaxy is approaching Earth, the wavelengths of light it emits become shorter. If a star or galaxy is moving away from Earth, the wavelengths of light are longer. Object receding, long red waves. Object approaching, short blue waves. In Figure 2, the wavelengths of light from a receding star or galaxy are stretched toward the red end of the light spectrum, while wavelengths of light from an approaching star or galaxy are shortened toward the blue end of the light spectrum. Scientists have observed that the wavelengths of light emitted by all galaxies, except our close neighbors, are being shifted toward the red end of the spectrum. The wavelengths at this end of the spectrum are longer. They have concluded that these galaxies must be moving away from Earth. Therefore, the entire universe must be expanding. Remember your model of an expanding universe from the Investigate? The dots, or galaxies on the balloon, moved apart as the model universe expanded. In a similar way, distant galaxies beyond our own and those close by are moving away from Earth. Figure 3 shows a map of the universe was created by the European Space Agency's Planck mission. It shows remnant heat left over from the Big Bang. Different colors on the map indicate extremely small variations in temperature. Let me leave this up as I talk about the next part. The galaxies and stars are the visible evidence of the Big Bang. However, there is other unseen evidence in the form of radiation. This evidence is called the cosmic background radiation, or cosmic microwave background. You examined a sky map of this evidence in the Investigate. If the universe began in a highly concentrated state with extremely high temperatures, then it would have filled with radiation. If radiation filled the universe back then, that same radiation should still fill the universe. Originally, the radiation would have been high energy and had short wavelengths, for example, visible light. However, as the universe expanded and cooled, originally, the radiation would have been high energy and had short wavelengths, for example, visible light. However, as the universe expanded and cooled, the radiation would have shifted to lower energy and longer wavelengths, for example, microwave energy. Using special instruments, astronomers have detected this radiation coming in from all directions of the universe. The existence of the cosmic background radiation is generally considered to be solid evidence of the Big Bang. The third line of evidence that supports the Big Bang theory lies in the abundance of the elements hydrogen and helium found in the universe. According to the theory, in the earliest moments after the Big Bang, there was nothing more than hydrogen compressed into a tiny volume with extremely high heat and pressure. At this point, the entire universe was acting like the core of a star, fusing hydrogen into helium. These reactions only lasted for a brief time as the universe's temperature and density were dropping rapidly as it expanded. This means that elements heavier than hydrogen and helium did not have a chance to form during this time. Instead, these elements formed later in the stars. Scientists have calculated that the initial period after the Big Bang would have produced a universe that is roughly 75% hydrogen and 25% helium. They have looked towards very distant galaxies that are billions of light years away, as well as old stars, to determine if this ratio is valid. Because of the time it takes for light from distant galaxies to reach Earth, they are seen not as they are, but as they were billions of years ago. Careful measurements of the hydrogen and helium of these very distant galaxies, as well as old stars, exactly match the 3-to-1 ratio of these elements in the early universe. The steady state theory. Let me scroll up a little bit. Okay. There is strong evidence for the Big Bang theory. However, it continues to be tested and examined. Another explanation is the steady state theory. It is also known as the infinite universe theory. This theory suggests the universe has always existed. It did not have a moment of creation or a time zero. The theory suggests that The theory suggests that new matter is continuously created out of empty space. The matter created out of empty space is mostly hydrogen. The rate at which new matter appears is in balance with the expansion of the universe. Therefore, the average density of the universe remains constant. There are arguments against the steady state theory. They include the discovery of the cosmic background radiation. As you read earlier, this radiation indicates that the universe did have a beginning. Just after the Big Bang, all that existed in the universe was energy. As the universe expanded, it cooled. About 300,000 years after the Big Bang, the temperature of the universe had cooled enough to allow atoms to form. Leftover energy from this moment can be observed today. This radiation comes from all directions in the universe. The steady state theory has also been challenged by the discovery that galaxies were more crowded together in the past. This is evidence that the density of the universe has changed over time. It is impossible to know for certain how the universe began. Today, the evidence is in favor of the Big Bang theory. However, one day scientists might make a discovery that cannot be explained by this theory. Scientists would then have to start looking for a new model of the origin and evolution of the universe. The fate of the universe. What will ultimately happen to the universe? Historically, cosmologists have considered three possible outcomes. It will expand forever, it will expand to a certain size and stop, it will stop expanding and begin to collapse. All three cases are based on the idea that the rate of expansion of the universe has slowed down since its beginning. Recall from the previous sections that galaxies are millions and even billions of light years away. It takes light a long time to reach Earth from faraway galaxies. When astronomers observe the most distant galaxies, they are observing the galaxies as they existed far back in time. These observations can provide an idea of what the universe was like when it was much younger. Scientists measure the extent to which light from these galaxies is shifted toward the red end of the spectrum. This helps them to determine the expansion rate of the universe in the past. They can then compare that rate to today's rate. Scientists are surprised by recent observations of the change in the rate of the expansion of the universe. Data suggests that the rate of expansion slowed for a while. Now it is speeding up. The current explanation for this change is that the universe is filled with an unidentified form of energy. That energy is causing the expansion of the universe to speed up. Scientists are calling this dark energy. Scientists are calling this energy dark energy. If these observations are correct, scientists think that the universe will continue to expand forever. In Figure 4, how the rate of expansion of the universe has changed over time. The nebular theory. If there was a Big Bang, how did the solar system form? When you made a scale model of the solar system in Section 1, you probably noticed how large the sun is in comparison to most of the planets. In fact, the sun contains over 99% of all of the mass of the solar system. Where did all this mass come from? According to current thinking, the birthplace of our solar system was a nebula. A nebula is a cloud of gas and dust. This particular nebula that gave rise to our solar system was probably cast off from other stars that existed in this region of our galaxy. More than 4.6 billion years ago, this nebula started the long process that led to the formation of a star and planets. The idea that the solar system evolved from such a swirling cloud of dust is called the nebular theory. You can see one such nebula in the constellation Orion, just below the three stars that make up the belt of Orion, as seen in Figure 5. Okay, there's the belt of Orion right there. Through a pair of binoculars or small telescope, the Orion Nebula looks like a faint green, hazy patch of light. Okay, and we'll kind of scroll down and learn more about that. Oh, I don't know if I read the description. Figure 5, Orion is a prominent constellation in the night sky. All right. If you were able to view this star birth region through a much higher powered telescope, you would be able to see amazing details in the gas and dust clouds. The Orion Nebula is very much like the one that formed Earth's star, the Sun. There are many star nurseries like this one scattered around our galaxy. On a dark night, with binoculars or a small telescope, you can see many gas clouds that are forming stars. In the nebula that gave birth to our solar system, gravity caused the gases and dust to be drawn together into a denser cloud. Figure 6 shows the Keyhole Nebula, which is imaged by the Hubble Space Telescope. Okay. On a dark night with binoculars or small telescope, you can see the many gas clouds that are forming stars. Okay, so nebula. All right. And this is the Keyhole Nebula. Alrighty. In the nebula that gave birth to our solar system, gravity caused the gases and dust to be drawn together into a denser cloud. At the same time, the rate of rotation or swirling of the entire nebula gradually increased. The effect is the same as when a rotating ice skater draws his or her arms in, causing their rate of rotation to speed up. As the nebular cloud began to collapse and spin faster, it flattened out to resemble a disk. Most of the mass collapsed into the center. You saw something similar when you sprinkled the creamer onto the hot chocolate. Initially, the creamer spread out over the surface of the liquid, but when you stirred the chocolate in a circular motion, the creamer clumped together in the center. Matter in the rest of the disk of the nebula clumped together into small masses called planetesimals. The planetesimals gradually collided together to form larger bodies called protoplanetary bodies. At the center of the developing solar system, material kept collapsing under gravitational force. As the moving gases became more concentrated, the temperature and pressure of the center of the cloud started to rise. The same kind of thing happens when you inflate a bicycle tire with a tire pump. As the air is compressed, it gets warmer and heats the pump. When you let the air out of the tire, the opposite occurs. The air gets colder as it expands rapidly. When the temperature in the center of the gas cloud reached about 15 million degrees Celsius, hydrogen atoms in the gas combined or fused to form helium atoms. This process, called nuclear fusion, is the source of the energy. This process, called nuclear fusion, is the source of the energy from the sun. A star, the sun, was born. Fusion reactions inside the sun create very high pressure. This pressure threatens to blow the sun apart. The sun does not explode under all this outward pressure, however. The sun is in a state of equilibrium. The gravity of the sun is pulling on each part of it and keeps the sun together. It radiates energy out in all directions, providing solar energy to the Earth community. The birth of the planets. The rest of the solar system formed in the swirling disk of material surrounding the newborn sun. 8 planets, more than 100 moons, and a large number of comets and asteroids formed. Moons are also called satellites. New moons are still being discovered today. 4 of these planets, shown at the top of figure 7, right here, Mercury, Venus, Earth, and Mars. Okay, Mercury, Venus, Earth, and Mars are called the terrestrial or Earth-like planets. They formed in the inner part of our solar system, where temperatures in the original nebula were high. They are relatively small, rocky bodies. Some have molten centers with a layer of rock called a mantle outside their centers and have a surface called a crust. Earth's crust is its outer layer. Even the deepest oil wells do not penetrate the crust. The larger planets, shown at the bottom of Figure 7, Jupiter, Saturn, Uranus, and Neptune, consist mostly of dense fluids like liquid hydrogen. These gas giant planets formed in the colder outer parts of the early solar nebula. They have solid rocky cores about the size of Earth. The solid cores are covered with layers of hydrogen in both gas and liquid form. These planets lie far from the sun, and their surfaces are extremely cold. There are trillions of comets and asteroids scattered throughout the solar system. Earth and other solar system bodies were scarred by impact craters. These craters were formed when comets and asteroids collided with them. On Earth, erosion has removed obvious signs of many of these craters. Astronomers see these comets and asteroids as the leftovers from the formation of the solar system. Asteroids are dark, rocky bodies that orbit the Sun at different distances. Many are found between the orbits of Mars and Jupiter, making up what is called the asteroid belt. Many others have orbits outside of the asteroid belt. Okay, so here's the asteroid belt between Mars and Jupiter. Okay. There's Mars, there's Jupiter, there's the asteroid belt. All right. Okay. Asteroids are dark, rocky bodies that orbit the Sun at different distances. Many are found between the orbits of Mars and Jupiter, making up what is called the asteroid belt. Many others have orbits outside of the asteroid belt. Comets are mixtures of ice and dust grains. They exist mainly in the outer solar system. However, when their looping orbits bring them close to the Sun, their ices begin to melt. That is when you can see trails streaming out from them in the direction away from the Sun. Some comets come unexpectedly into the inner solar system. Others have orbits that bring them close to the Sun at regular intervals. For example, the orbit of Halley's Comet brings it into the inner solar system every 76 years. Figure 7 is a composite image of the planets in the solar system. Okay. Figure 8. Two diagrams are required to show the orbits of the planets to scale. Extrasolar planets. Have you ever looked up at the sky and wondered whether there are planets outside of our solar system? Planets orbiting stars other than the Sun are known as extrasolar planets. To date, astronomers have found hundreds of such planets, and new discoveries are made every month. All of the extrasolar planets discovered so far are in our galaxy. See Figure 9. So here's Figure 9. Here's Figure 9. All of the known extrasolar planets are within the Milky Way galaxy, our planet hunting neighborhood. Most of the planets found to date lie within about 300 light years from our Sun. Okay. Finding extrasolar planets is difficult. Distant planets are often masked by the light of the star that they revolve around. A star can be millions or even billions of times brighter than its orbiting planets. For this reason, it is almost impossible to observe these planets directly. Instead, astronomers gather indirect evidence of their existence. The most common technique is to analyze a star's light. As a planet orbits a star, the planet's gravity tugs on the star. This causes the star to move away from and toward Earth slightly as the planet orbits the star. Due to the Doppler effect, This small movement affects the light emitted by the star. When the star moves away from Earth, the wavelength of the light becomes longer. When the star moves toward Earth, the wavelength becomes shorter. This change in wavelength results in a change in the color of the light. The change in the color indicates that a planet is pulling on the star. This provides indirect evidence of the existence of a planet. The hundreds of extrasolar planets discovered so far are extremely varied in terms of their physical properties and orbits. Most are gas giants, but a few terrestrial planets have been identified. Many are extremely hot because of a close orbit to a star. Some have an orbit that is very distant from the star and are icy cold. Some orbit massive stars many times bigger and more brilliant than our sun. Others circle dim stars that are much smaller than the sun. Most extrasolar planets that have been identified are Jupiter-like gas giants. The largest extrasolar planet found to date is HD 43848b. This planet is about 120 light years away. It has a mass equal to 25 Jupiters. It has an orbital period of about 2,371 days. The smallest extrasolar planet to date is Gliese 581e. It has a mass equal to 1.9 Earths and an orbital period of 66.8 days. This planet is over 20 light years away. Some astronomers believe that eventually the discovery of small planets will outnumber giant planets. Some of these small planets will probably resemble Earth. Figure 10 shows disc-shaped clouds around Vega, debris disk around Vega, Spitzer Space Telescope, MIPS. Okay, and I just looked up because I wanted to make sure that I defined what this abbreviation or acronym is, and it's the Multiband Imaging Photometer from the Spitzer Space Telescope. Okay. All right. Scientists have discovered stars that do not have any planets, but our solar system's in the process of forming. Vega, the brightest star in the constellation Lyra, I think that's up here. Okay. Let me zoom out a little bit so I can read this while you're looking at the image. Okay. Vega, the brightest star in the constellation Lyra, is one example. Beta Pictoris, a star in the southern constellation Pictor, is another. Both have disc-shaped clouds around them, as described in Figure 10. Scientists believe these disks are massive, rotating clouds of dust and gas. These clouds of dust and gas could eventually form planets. This is much like how our solar system formed. Let me zoom back in. Not all the newly discovered solar systems fit this pattern. A recently identified young solar system shows a different pattern. The inner part is orbiting in one direction. The outer part is orbiting in the opposite direction. No planets have formed yet. However, eventually this system could have planets orbiting in different directions. This pattern of the orbiting planets would be different from our own solar system. Laws, theories, and the Big Bang. Sometimes the meaning of a word in science is different from its everyday meaning. For example, you may say that you have a theory about something when you mean you have a hunch or a guess. You also may say that you obey the law, referring to laws that are written and passed by a government. However, in science, the words theory and law have very different but precise meanings. However, in science, the words theory and law have very different but very precise meanings. In their observations over long periods of time, scientists often notice certain patterns that occur over and over again. From these observations, they develop a scientific law to describe the patterns they have observed. For example, over time, scientists observe that each object in the universe attracts every other object with a force that is related to the mass of the objects and the distance between them. Newton stated this as the law of universal gravitation. This law does not explain why all objects experience this force of attraction, but provides a way of describing what has been observed. A scientific theory provides an explanation for those observations and can be used to predict new phenomena that have not been observed. For example, the Big Bang Theory explains the development of the universe. This theory is not a hunch or a guess. It is the result of years of experiments, observations, measurements, and mathematical applications. The work of many people over many years culminates in a theory, and the subsequent work of many people in many years is required for acceptance of that theory in the science community. Though related, laws do not become theories, and theories do not become laws.